When a massive star exhausts its fuel, gravity takes over. The core implodes, compressing into a dense point in space. To analyze this collapse, physicists use a mathematical grid called a metric. This is a 4x4 matrix that describes how mass and energy warp the geometry of space and time. These rules were established by Albert Einstein's field equations. However, because the equations are nonlinear, finding exact solutions that describe real-world conditions is a significant challenge. In 1915, Carl Schwarzschild found the first exact solution for a black hole. To make the calculation possible, he assumed the system was static, meaning the black hole had no electric charge and did not rotate. But the real universe is dynamic. Stars spin, and matter within them carries charge, which meant Schwarzschild's description could not account for most celestial bodies. Physicists realized that a complete mathematical model of a collapsed star requires only 3 external properties. This is the no-hair theorem, the principle that mass, charge, and spin are the only variables needed to define a black hole's exterior. We can assemble this model by adding those variables one by one, beginning with the baseline of mass, or m. In the Schwarzschild solution, mass warps the metric to create an event horizon, a point of no return, and a single central singularity of infinite density. The second parameter is electric charge, or Q, described by the Reissner-Nordström metric. Adding charge changes the black hole's internal geometry. The math requires a nested structure, generating a distinct inner horizon inside the primary event horizon. While charge adds internal complexity, these models still fail to account for rotation, which is a near-universal trait of cosmic objects. That requires the third parameter, spin, or J. This was not solved until 1963, when Roy Kerr discovered the metric for a spinning mass. Rotation twists the surrounding fabric of space, creating an oblate, pumpkin-shaped boundary called the ergosphere that sits outside the event horizon. This creates a whirlpool of space, where all objects are forced to rotate in the direction of the black hole's spin. This effect is called frame dragging. It was physically verified by the Gravity Probe B experiment, which measured a similar, though smaller, twisting of space caused by the rotation of the Earth. Spin also changes the center of the black hole. The singularity is no longer a point. The rotation stretches it into a flat ring located on the equatorial plane. In 1965, Ezra Newman's team succeeded in integrating mass, charge, and spin into a single solution. They used the Newman-Jonas algorithm, a method that uses a complex coordinate transformation to derive the spinning, charged metric from the static Reissner-Nordström solution. The resulting Kerr-Newman metric is the most general stationary solution to these equations, describing a black hole with an ergosphere, dual horizons, and a charged ring singularity. In a practical sense, real black holes are unlikely to hold a significant electric charge. They typically neutralize by attracting matter with an opposite charge from their environment. This raises a question. If highly charged black holes don't exist in space, why is this specific metric so important to modern physics? The answer lies in the gyromagnetic ratio, the relationship between magnetic moment and angular momentum. For a Kerr-Newman black hole, this ratio is exactly 2, which is the same value Dirac calculated for a subatomic electron. This means the mathematical description of a massive celestial object yields the same ratio found in a fundamental quantum particle. This overlap provides a mathematical intersection between general relativity and quantum field theory. It is a rare instance where the equations for a massive star align with the properties of the subatomic world.